Hello, everyone. This is the lecture for section 4.5 for Math 210, derivatives and the shape of a graph. So this is a pretty heavy-hitting section in terms of the applications of a derivative, okay? We know sort of conceptually and fairly rigorously what a derivative looks like on a graph, right? We know that that is two things, right? Depending on how we want to use it, right? One of the ways that I defined it was the instantaneous rate of change at a point x equal a, right? And the other one is the slope of the tangent line, right? At a point x equal a, right? Okay. What we're going to look at now for this section in particular, right, is what those two things can do for us, right? In particular, what a derivative can do for us if we need to analyze the shape of a graph, or how, in more sort of in more of an applicable sense, right, the behavior of a function dependent on that x value, right? And we're going to be using the derivative to figure out what that behavior is, okay? So that is what we're going to be doing for this section. So the first thing I want to start off with is there's three things that I'm going to cover in this section, okay? That'll help us out with sort of determining behaviors of functions, okay? The first one is what we call the first derivative test, okay? The second one, which will come up later, and these last two are ones that are used usually sort of in tandem with each other, right? You don't use one over the other, you kind of use both at the same time. The other two are the test for concavity, okay? And the second derivative test, okay? Let me start with first derivative test first, okay? So the first thing I want to define, okay, show you guys is this thing right here. That's this first derivative test, okay? And it has two parts to it, okay? So suppose you have a function, okay, that the first derivative at a value c, right, is greater than 0. Then what we can say is that the function is increasing, okay? So for example, let me go ahead and draw a picture here, right? So let's say this is my function right here, right? So it doesn't matter which one it is. It can be increasing like this, or it can be increasing like this. So both of these can be considered my f of x, right? Okay? Notice that all of these slopes, I'm drawing them in green lines for a reason. You see all these slopes, they are positive. They are in increasing slopes, right? Okay. So what I want to say here, right, is f prime, right, is bigger than 0 for all of these. The slopes are positive, right? Okay. The reverse is also pretty easy to understand. If your function is decreasing, right, then the first derivative at those values is going to be less than 0. Okay, so again, it doesn't matter how it's decreasing. It can be decreasing like this, or it can be decreasing a lot sharper, right? If you take a look at all the tangent lines, those tangent lines are negative. Negative, negative, negative. Got it? So this means, right, all of these, the derivatives are going to be 0. Or less than 0, sorry. Got it? Okay. This is all we really need for the first derivative test. Okay? This is all we need for the first derivative test. Okay? So let me explain what we're going to get here. Okay? And let me read them out first. Okay? Suppose that you have a function f of x that is continuous, so you can draw your line without picking up your pencil. That's the sort of the quick and dirty, right? Suppose that you have a function that you can draw without lifting your pencil, okay? and it contains a critical point. Okay, so if you guys remember a critical point, right? I'm going to write it up here, right? C critical point, right? Means, let me get rid of, I want to get rid of that one little comma that I have right there. Critical point means, right, that f prime of c is equal to 0, right? Or f prime of c is undefined or does not exist. Okay, just a quick review. Okay, so suppose you have a function and you look at this function over an a to b. Okay, and somewhere in there you have a critical point c. Okay, then you're going to have one of the following three things happen. Okay, one, two, three. For the first one, if f prime, if your derivative changes sign from positive before your value c to negative after c, okay, then you have a maximum. Okay. Second, number two. I'll illustrate these in a second. That's what the squares are for, right there to the right. Okay. Uh, suppose, right, your f prime, so your derivative, changes sign from negative before c to positive after c. Okay. Then what you have is a minimum. Okay. If you have the exact same sign before and after C, right, then you have neither a local maximum or a local minimum. You learn what those are once you get to Calc 3. So for now, number 3, that one we're going to sort of just say it's neither local min or max. Okay? All right, so now the illustration, right? So let me do the maximum first, right? And then over here, I'm going to do a minimum. Okay, so suppose, again, right, here's your axes, right? So a y and the x, and you have a function that does that, right? So hopefully you guys see that right about there. I'm going to drop a, bam, c. There's my critical value. Okay, notice what happens with the slopes before and after c. So before c, right? Hopefully you guys see this, right? I'm going to do a bunch of tangent lines here. All of these slopes are positive, right? And they're getting smaller. They're getting flatter and flatter, right? And then afterwards, those slopes are trending downward. They're negative, right? So notice what happens here, right? F prime is equal to positive values on this side, okay? And f prime is equal to negative values on this side. If that happens, okay, we have a maximum. Okay. Same analysis happens for a minimum, right? Now that you start looking at the derivative as the slope of the tangent line. So again, I'm just going to do my two axes, y and x. Okay. Here's my f of x. And here's my critical value c. Yeah. So again, look at the slopes, right? Before c, all of these slopes are negative, and they are transitioning toward positive slopes on the other side. So before the critical value, we have f prime equal negative values, right? And afterwards, we have f prime equal positive values. Whenever this happens, okay, we have a local minimum. Got it? Okay, awesome. Now, notice what we did here. We were just looking at slopes of tangent lines, right? And we're able to get this kind of test, right? What comes up next, right, just from first derivative test, what we get is a pretty darn good problem-solving strategy for determining what the heck a function does, right, over a specific interval AB. Okay? And all it uses is first derivative test. So, the 3 steps for the problem-solving strategy are as follows. Okay? Step 1, find all critical points. Okay? And we're going to divide our interval into smaller intervals, right, that use the critical value as endpoints. Okay? Part 2, we analyze the sign of f prime. We're going to analyze the sign of f prime. We do need to evaluate, but we don't really care about the value itself. We care about the sign, whether or not the number is positive or negative. Okay? And then third, we use the results from the first derivative test, the thing that's right above here, okay, to determine local extrema, whether we have a maximum or whether we have a minimum. That's simple. Okay, so the running example that I'm going to be using for this section is this function right here. So I am, in particular, okay, for this section, we will graph it. I will graph this function eventually, just not right now. Got it? We are going to try to analyze this without looking at the function first. Got it? Okay. So the idea, I'm going to use first derivative test to determine where the local extrema are. Okay. We need to first find the critical values. Okay. So I'm going to go ahead, and in order to find critical values, right, I need to find the derivative, right? So f prime of x means I need to take the derivative of that. Okay. Notice that that is a product, so I need product rule, right? So I'm going to do a first and a second. Let me go over here. First prime is 2x. Second prime is e to the x. So we're off to the races, right? So my derivative is going to be the first times the derivative of the second. So x squared ex plus the second times the derivative of the first, 2x ex. Okay? So now notice, I can clean this up a little bit. Both of these have a x and an ex in common. You guys see that? So this has an x, an ex, ex. So what I'm going to do is I'm going to pull out x, e to the x, okay? And what gets left behind is that, okay? To find, right? To find the critical numbers, right? To find the critical numbers, f prime is equal to 0, or, right? Wrong type of f. F prime of x equal does not exist. This one doesn't happen. Actually, let me grab this. I'm going to move this over here. I should have moved it with the or as well. There we go. What a time to be alive, right? There we go. Okay. So define the critical values. F prime equals 0 or f prime does not exist. In order for f prime to not exist, right, I have to be doing one of the bad things, right? I can't be dividing by 0. I can't take the square root of a negative, and I can't take the logarithm of a negative, right? Since I'm not taking the logarithm of a negative, I don't have a logarithm in my derivative. I don't have a division in my derivative, right? And I don't have a square root in my derivative. So this one is sort of out the window. This one is out the window. The only one that we really need to check is this one, that the f prime is equal to 0, right? So then I'm going to go ahead and do x e to the x times x plus 2. I need to find out when this is equal to 0, okay? These are all multiplications, right? If I have a string of multiplications and it's equal to 0, that means one of the things is equal to 0, right? So either x is equal to 0, e to the x is equal to 0, or x plus 2 is equal to 0, right? One of these can't happen. This one. Whoa, not what I want to happen. Why does it do that? E to the x is equal to 0. So this one is the one that can't happen. Whoosh. Right? E to the x is an exponential. It sits above the x-axis all the time, so that can never drop down below 0. So the only two that are left are x equals 0, in which case that's one of our answers. And the other one is x is equal to negative 2 from this one. Are we good? Cool. All right. Here comes first derivative test. And I think you might want to have the list for the problem solving strategy, the thing that's right above this, close by so you guys can follow along about what I'm talking about. Okay. What we're going to do now is we're going to, like the steps say, right, analyze the sign of f prime over each subinterval. So now what's the subinterval? They were supposed to be the subintervals that were coming from my critical values. So what I'm going to do now is this. There's going to be, I'm going to make a, going to be a number line. I know it's been a long time since we've seen one of these, right? Okay. And the number line is going to be made from our critical values. It's going to be 0 and 2. Whoops, actually I got them the other way around. Negative 2 and 0. Okay? Now, those are our critical values. What we're going to do, here's my division of the number line using my critical values. There's going to be an interval before negative 2. There's going to be an interval between negative 2 and 0. And then there's going to be an interval everywhere above 0. Okay? What we're going to do, okay, is we're going to grab some test points. Okay? I want a test point somewhere before negative 2. Okay? And you can really make it whatever you want. I will want to sort of warn you or just sort of suggest to you, make your life easy, right? Choose nice numbers. So a nice number I'm going to choose over here is negative 3. And I'm going to make them in this orangey color. Okay? I'm going to do the same thing for this range right here, the one that's between negative 2 and 0. I'm going to choose a nice number, negative 1. Okay? And then over here, I'm going to choose another number. Again, make your life easy, right? Make the math easy. Numbers really close, nice whole numbers that are really close to those values really do help. Got it? Okay. We're getting somewhere. We're getting somewhere. And I'm going to be looking at, right, f prime of x. This function right here. I'm going to highlight it in pink for now so we know what we're following along with, okay? And what I'm going to do is I'm going to grab these test points, these three, 1, 2, 3, and I'm going to throw them into f prime of x. Okay, I'm going to back this off a little bit because I think I'm going to need the space to write. Okay, I'm going to plug them in to my f prime of x. I'm going to plug them into my derivative. Okay, and what I really care about is not particularly the value, it's the sign of the value that I care about. I just need to know if it's positive or negative. That's it. Okay, so if I grab -3, whoa, if I grab -3 and plug it into f prime, I'm going to get this. -3 e to the -3 times -1. Okay? If I do the same thing with -1, I'm going to get -1 e to the -1 times 1. Okay? And if I plug it into, if I plug 1 in, I get 1 e to the 1 times 3. Okay? And just real quick, right? I am plugging these into this right here. I'm plugging it into this function right there. Okay. Now, like I said, I don't care about the values themselves. What I do care about is the sign of the values. So if I take a look at each one of these, so if I take a look at this, okay, I've got a -3 times a -1, that's going to be positive, right? And e to the -3, e to the -3 is still positive. So I have two negatives that make my positive times another positive. This sign is going to be positive. Okay? For the next value, this one, okay, I have a -1 times 1. Okay, that is going to still be negative, and e to the -1, that's still positive, right? So I have a negative times a positive times a positive. This is going to be negative. This is going to be a negative. Okay, and then the last one, right? I have e is positive, 3 is positive, 1 is positive, right? So this is going to be positive. So this value right here is going to be positive, whatever it is, right? It's just going to be positive. All right, we're getting somewhere. So now what I'm going to do is this. I'm going to use my blue pen because I'm dragging down those two critical values. Okay. We know that those two critical values, right, there's either going to be a maximum or a minimum there. Okay. And what we're going to do here is we're going to be using that number line that we just created. We're going to be using that along with the positive, negative, positive that we just have, right, that we just figured out to determine which one we do really have, either a maximum or a minimum. Okay, so looking at these two, okay, at x equal -2, the slopes before are positive, right, which means that our function is increasing. And then our slopes afterwards are negative. So that means our slopes are decreasing after 2, right? If you go back to the very beginning of the section, right? Slopes positive before, negative after, that is considered a maximum. So At -2, we have a maximum. Got it? Okay. I'm going to do the exact same analysis on this side over here for at x equals 0. Okay. Before 0, the slopes are all negative. So my function is decreasing. After 0, my slopes are positive, which means my function is increasing, right? Whoops, not -0. Come on. Okay. Slopes negative before, slopes afterwards are positive. That is a minimum. There we go. So notice what we did. Just using the derivative, okay, we're able to determine whether or not we have maximums or minimums. We don't know particularly how high or how low these maximums or minimums go, but we know that we have something that looks like this, right? We have something that looks like this for the first one and something that looks like that for the second one. Okay? There we are. There we are. Okay. So what I'm going to have everybody do now, some quick checks. Use the first derivative test. Try not to graph it. Try your very hardest. I know this is going to test your patience. Try very hard not to graph it. Just use the derivative to figure out whether you have a max or a min at your critical value. So that means you're going to need to take the derivative, right? Set it equal to 0, find your critical values, and then do the table, do this little number line gimmick that I did just here on the right-hand side of the screen, right, to find them out, okay? I'm going to give everybody a good amount of time in class to figure this one out, okay? All right, moving right along. What comes up next is concavity and inflection points, okay? So, max and mins, we use first derivative. Okay, concavity and points of inflection, for this one, we end up using the second derivative. Okay. All right, so first of all, what I want to do is define some stuff that we're going to need, some terminology that we're going to need to sort of, start to describe whatever our function is doing, right? Okay. So suppose your f of x is differentiable over an interval, okay? If f prime is increasing, okay, then we say that f is concave up over an interval I. Okay, if f prime is decreasing, okay, we say that f is concave down. Okay, so remember our second derivative, right, is the derivative of the derivative. Okay, and remember that the first derivative is a rate of change, right? So that means the second derivative is the rate of change of the rate of change. Got it? AKA, right? Another way to say this, right, is the second derivative is giving us how quickly f prime is changing. So how quickly the slopes are changing. Okay? So let me go over here. Something that is concave up. Let's do concave up first. So Yes? So concave up means it's bowl up, right? And concave down means it's bowl down, like that, right? Okay. What I want everybody to look at is the slopes of the tangent lines as we go across each one of these shapes. Okay, so notice what happens here, right? These slopes for concave up, they are all negative, yes? But look at what happens uh, as we go along, right? So here, these are steep, right? Over here, they're less steep. Over here, they're still negative, but almost flat. So they are going from big negative, right, to small negative. And then eventually what's going to happen on the other side, right, if you can take a look at this, right, is whoosh, right? Whoosh, whoosh. Okay, so down here, they're flat positive, right? But they're positive. They're flat, but they're positive, right? And over here, they go more steep. And over here, way over here, they're very steep, right? So if we take a look at the definition that I just provided over here, right, we can see that the slopes of the tangent lines, the f primes, okay, the f primes, they're going from big negative to big positives, right? Whenever that happens, we have something that's concave up. The absolute opposite, exactly the opposite, will happen for a concave down. So notice what happens over here. These slopes are very steep positive, and they're heading toward sort of flat values, right? Still positive, but they're heading toward smaller positive values. And then once you cross that maximum, once you cross that maximum, those slopes become negative. They start out very small negative and start going to very big negative. Yes? So over here, very steep, right? Over here, very flat, but positive still, right? And then once you cross that maximum, right, they go from very flat to very steep negative. Hopefully the colors aren't tripping you out. Got it? All right, here we go. So now let's move on for the second of the tests for this section. It is the test for concavity. Okay, so I'm going to go back over here. This one's going to be the concave up. And the second one's going to be concave down. Okay, suppose you had a function, right, that is twice differentiable over an interval AB. Okay, let me do concave up. So whoosh, and then concave down, whoosh. Yes? Okay. As we go this way, come on, come on. There we go. As we go this way, right? Notice what's happening. My slopes are going from negative to positive, right? So we say here, right, f prime is growing. My f primes are positive, which means this exact thing. My double prime is bigger than 0 for all the x values for something that's concave up, right? If that happens, then you know it's bowl up. It's going to be concave up, okay? Likewise, okay, if you go that way, right, my f primes are decreasing because they are starting big positive, right? These are big positive values. And then they're going toward negative slopes. So my f primes are decreasing. Whenever that happens, right, we're saying my f double prime over any one of these points is less than 0 for all x values here. If that happens, we have concave down. We have something bowl down. Okay? New definition. An inflection point. Okay? An inflection point is considered a point where your f of x changes concavity. Okay? And that happens whenever the second derivative is equal to 0 or when the second derivative is undefined. So it's exactly the same idea for the definition, at least, right, as the critical values, right? So remember when critical values is when the first derivative is equal to 0 or when the first derivative is undefined. Inflection points are when the second derivative is equal to 0 or when the second derivative is undefined. Okay, how would they look like on a graph, right? So in your graphs, right, you're going to have something that does this, right? And then it might transition into something like that, right? And actually, I didn't give myself enough room here. So something concave up, changing to concave down. Okay, you can see that there's a point right there, right? And then vice versa, we can have the other way. We can have something that goes like this and turns into something that looks like this, right? So something, whenever both of these points, right? Both of these points are inflection points. Whenever your function changes concavity, uh, that's what we call an inflection point. Okay, and they're found by first derivative equal to 0 or first derivative undefined. Sorry, second derivative uh, equal to 0, second derivative. You guys see how easy it is to confuse these things? Okay, just make sure you write them down on your flashcard. Okay, this test and the one that I'm about to present tend to be used hand in hand. You don't have to use both of them sort of independently for any one problem, right? You can use one to verify the other. That's actually what tends to happen more often than not, okay? It's the second derivative test, okay? So suppose, let me write them in first. On the first one, I'm going to do max, and on the second one, I'm going to do min, okay? All right, here we go. Suppose you have something, so suppose your second derivative, right, is bigger than 0 at a critical value. So here's your function. We know that this is going to be a critical value right here. And I forgot to put my x and y. x, y. You guys see how we know, whoops, and I'm doing them backwards. This is going to be minimum. And this one's supposed to be maximum. Okay. We know that that's going to be a critical value. So we know it bottoms out or it tops out, right? Okay. Notice what happens to the slopes, right? The slopes are going from, as I go this way, right? F prime is increasing that way, right? So that means F double prime has to be bigger than 0. Okay? If that happens, we know that we have a local minimum there. Okay? Next one. If your double prime is less than 0, okay, so same idea of a picture, right? X and Y, but this case we have this, we have max. We know that this is a critical value right there. That's my C, right? Okay. Notice that as we go this way, right, F prime is decreasing as we go that way, right? This says, right, that F double prime is less than 0. Whenever that happens, we have a local max, okay? And then the last one, like I said, you'll learn this eventually if you end up getting, if you need to end up taking Calc 3. This has a special thing when the derivative, when the second derivative is equal to 0 in particular. For now, for this class, it is inconclusive, okay? We do have a special name for it, but we'll show you guys that later if you need to get to Calc 3. Got it? All right. How is this used sort of in practice? Kind of, right? We might need to be able to determine concavity or inflection points, changes in concavity, okay, of a function. Okay, I'm going to use the same function that I've been using over the last couple of examples here. Okay, so what I'm going to do here is I'm going to determine uh, concavity and inflection points for that function right there. Okay, now I'm going to write down some stuff here. So f of x, I'm going to start with the regular, so x squared e to the x. From first derivative test, we know what f prime was. Okay, f prime was x e to the x times x plus 2. Okay, okay, this is a prime right there. For test for concavity and for second derivative test, we need the second derivative, right? So that means we need to take the derivative of the derivative. You can believe me if I tell you, okay, the second derivative, if you clean it up right, and I would suggest you guys carry this out on your own, right, is going to be e to the x, x squared plus 4x plus 2. Got it? Okay. If you need to stop the video and double check this second derivative, right? So what I'm doing here is I'm grabbing this one, okay, and taking the derivative. And it gets me this. Okay? Whoa. Not what I wanted to do. There we go. Ah, I hate when it does that. There we go. Okay. Now, I need to determine whether or not, well, I need to determine where my inflection points are before we start doing concavity, right? So what I'm going to do is this. Right? F double prime is equal to 0, or F double prime is equal to does not exist. So I'm going to go ahead and handle the first one. The F prime does not exist. You guys remember for F prime, for something to not exist, I got to do one of the three bad things, right? I have to be dividing by 0. I have to be taking the square root of a negative, or I'm taking the logarithm of a negative. We have the same issue here, right? I'm not taking there's no square root in my F double prime. There's no division, so I'm not going to be dividing by 0. And there's no logarithm, so I'm not going to be taking the logarithm of it. So I'm good to go. This one, we don't have to worry about. Whoosh. So the only one that I really do have to worry about is when the second derivative is equal to 0. So that means that I'm looking for when this F double prime of x is equal to e to the x squared plus 4x plus 2. I need to find out when that thing right there is equal to 0. So if you guys remember how this works, right? Either e to the x is equal to 0, or x squared plus 4x plus 2 is equal to 0. Okay? This one can't happen. E to the x can never be equal to 0. E to the x is the exponential, right? And it's always above 0, so it'll never be 0. So the only one that will possibly get us equal to 0 is this one. Okay, if you remember back from our pre-calc stuff, right? How do we solve when this is equal to 0? Quadratic equation. I need to solve this out. Minus 4 plus or minus the square root. 4 squared minus 4, 1, 2, all over 2 times 1. And if you reduce this down, okay, I'm going to give you guys the two values, okay? Minus 2 plus the square root of 2, minus 2 minus the square root of 2. Now, these are the nice versions of both of those values if you solve for the positive and the negative, right? Okay, and I'm going to give you the numerical values for each one of these. So this first one is going to be negative 0.585, and the second one's going to be negative 3.414. Okay, so we have two inflection points, and they happen at those x values. Sort of draw an arrow down that way. There we go. Okay. So what I want to do first is I want to illustrate second derivative test first, and then we'll do test for concavity afterwards. The test for concavity is the one that's a little bit more the test for concavity is the one that's more explicit for how to determine behaviors of a function, right? The second derivative test sort of, for the most part, just confirms some stuff from your first derivative test. That's it. So that's why I want to do the more useful one last. Okay. So the first one I'm going to do second derivative test. Okay, so if you go back to second derivative test, okay, and look, suppose you had critical values, okay, and you plugged in the critical values into the second derivative and just looked at the sign, then it was going to tell you whether or not you had maximums or minimums. Got it? So I'm going to relist. There were two critical values, x equals 0 and x equal -2. Okay? What second derivative test states is that if I plug those into my second derivative, so f double prime of 0, and I just look at the sign, right? It should tell me whether or not I have maximums or minimums. We have that already figured out. So this is just sort of like confirming stuff from first derivative test. Okay? If you do that, if you plugged in 0 to the double prime, you get 2. Okay? This, if it's positive, right, says we have a local minimum. Okay, go back up to first derivative test. That is exactly what we found out. Okay, if we plugged in f double prime of -2, if we found the double prime of -2, -0.2707, that is a negative value, right? You go back to second derivative test. If it's less than, right, we have a local maximum. It's the same result that we got from first derivative test, right? It's a helpful thing sometimes, but usually if you went through first derivative test, right, you already have this information. This is sort of just repeating information you already have. That's it. Okay. The real useful one, right, is the test for concavity. That's the more important one. Okay. And the test for concavity, that one actually works out the same way that we did first derivative test. But we're going to do this. We're going to do the exact same analysis. Okay, exact same analysis. But we're going to be using our second derivative instead of the first derivative. So we have this going on. I'm going to do the same thing that we did before. Okay, a number line. Make it nice and long. Okay, and the two values that I'm going to put for this number line is my inflection points, which we found. It's these two, that one and this one. So -2 minus the square root of 2, and the other one is -2 plus the square root of 2. Now, I gave some computational numbers so we can play around with them a little bit, right? Okay. What happened after this point, if you remember how first derivative test worked, right, is we ended up choosing test points, right? Again, make the test points nice for yourself, okay, so that the math is easy, okay? I chose these. Before, I chose -4. In between, I chose -2. And then after, I chose 0. Okay, and like I said, I am concerned with f double prime of x at these three values. At this value, at this value, and at this value. Got it? Okay. And I'm plugging it into, and I'm going to color this, and I'm going to change my color for this. I'm going to need a purple. Here's my double prime. This is the double prime that I am concerned with when I do this. Okay? All right, here we go. If I plug in -4, my value is going to be e to the negative fourth times 2. If I plug in negative 2, I'm going to get negative 2 e to the negative 2. And if I plug in 0, I'm going to get e to the 0 times 2. Okay? Now, if you remember how this worked, in when we were doing first derivative test, right? Uh, we only care about the sign, really. Okay? Yes, these have values, they're numbers, right? But what we really care about is just the sign, whether or not it's positive or negative. Okay? If you take a look at this one, we can tell that this is positive. Okay? The next one over, this is clearly a negative number, right? And then the one that's afterwards is positive. Got it? All right, we're getting somewhere. So now I'm going to grab, just like I did before, I'm going to grab my inflection points. Right? And I'm going to go ahead and start analyzing this thing. Okay? So we know that the inflection points, these points right here, right? They are where our concavity is going to change. Our concavity is going to change. Okay? And we have the signs for before and after each one of these inflection points. We should be able to determine what the concavity is. And it's just exactly how you think it is, right? Everything before, right? So this is going to be an inflection point. Equal minus 2 minus root 2 x equal minus 2 plus root 2. If it's positive, okay, if your second derivative is positive, according to test for concavity, right, you have concave up. So this thing is going to be bowl up. Before that very first inflection point. Got it? In between the two, since it's negative, it's concave down. And then afterwards, since it's positive, concave up. Bam. Okay? This is a lot of work. This is a lot of work. Okay. What comes up next? Some quick checks. We are going to continue with the examples that we had from the very beginning. I want you all to go and determine, again, do not graph these on Desmos yet. Do not graph these on Desmos yet. What I do want you to do, right, is find the inflection points and try to determine the concavity without graphing it yet. Okay? I know you guys are probably getting a little impatient. Try to do it without it. Okay? Sound good? Okay. So now, this is why this is super useful stuff. What I'm about to do, okay, is I'm going to try, again, without a calculator, okay? I'm going to try to use the first derivative test, the test for concavity, and the second derivative test to try to provide myself a decent sketch of the function that I've been working on over the last 2-3 examples. Okay? So this might seem like cheating, right? Because I'm not going to redo the work. I've already got it here. So I copy pasted it over. Okay? Here is first derivative test results. Okay? And then I'm going to go over here and I'm collecting the test for concavity second derivative test results from that example. Okay. All I'm doing here, right, is I'm just uh-oh. All I'm doing here is just going back to my notes, right? Come on. Come on. It's being clumsy. There we go. I'm just grabbing my information from examples that I already did. That's it. Okay. And I should, whoa, okay. And I should put here first derivative test. Okay. I've got a couple values that I need to give you, okay, for critical values. Okay. Uh, x equals 0, x equal -2, .541. And then inflection points, we have x is equal to -2 minus √2, x is equal to -2 plus √2, -2 minus √2. Let's do that one first. 0.191 f of -2 plus √2. I got them backwards. 0.191, and this one is going to be 0.384. Okay. These. I'm going to use an orange. These give us our points, exact points, on a graph for both our critical values and our inflection points. Got it? And we've got our results from the first derivative test and test for concavity. So I'm going to try to grab all this information. I'm going to try to grab all this information. And I'm going to try to slap down somehow, some way. I'm going to zoom out a little bit so I can get the entire graph. There we go. I'm going to try to slap down a working version of all of this information so that it all sort of comes together. Okay? Okay, so what I'm going to do is I'm going to grab those points in orange. I'm going to put those down first. Okay, so I have critical values at 0 and at -2. No one at 0 should be right. Actually, let me do it in a little brighter of a color. Let me do the hot pink. 0, 0 is going to be 1 point. And -2, and what is that? A little bit more than a half, so maybe like right here. Okay, we have 2 inflection points. Okay, my x values for the inflection points, I should put that down. The first one, I'm actually going to go ahead and just keep them at the hot pink. The first one is -0.585. So -0.585. So let's see, 1.585, and trying to make sure I'm getting this right so I don't lie to you guys. That looks to be 0.19, so about 0.2, maybe right here. Whoa, come on. There we go. Okay, and then the next one is -0.585. negative 3.414 and 0.384. Negative 3.414, so that's about halfway across, right? And it should go up to 0.38, so about 0.4, so about right there, maybe. Okay, so I just graphed all four of our points, our two critical values and two inflection points. Now I'm going to use my first derivative test and second derivative test to try to graph this thing out. Okay, we know that this one from first derivative test, right, is a maximum. So it should sort of do something like this. Whoa, not what I wanted. And it's going to do that. Of course it will. All I wanted to do was erase one thing. Not everything, but just a little bit. There we go. Let me zoom out again. There we go, so I can have the whole graph present. Okay. We know that that one's a max. Okay. And then we also know that the one at 0, 0 is a minimum. Oh, come on. This one's supposed to be a minimum. Okay. And we know that these other points, right? Let me write that down right here. This is minimum. This is supposed to be an inflection point, right? And this is supposed to be an inflection point. Particularly, right, back here, from this point back, from the test for concavity, we know that that's supposed to be bowl up somehow. Got it? So over here, we're supposed to get this. It's supposed to look like that. Okay? So I'm going to start to try to add that in. I'm going to try to add it in a blue. Hopefully you guys see how what I'm trying to draw here is, right? And actually, I'm going to dip it down a little bit. Just, something like that. Got it? After that point, after that very first inflection point at about 3.5, it changes to cup down. It changes to bowl down, right? So I've got to connect this to this one, and you guys see how I'm doing it. It's now dropping instead. Oh my God. Now it looks like it's going to bowl down. Yeah? It's got to go through this other point right here. After this second inflection point, it has to bowl up, correct? And it's got to go through this minimum. So it should do something like this, right? And then afterwards, since it just stays bowl up, this end should just, I don't know, shoot up that way. So my final graph. And I'm going to do this in a nice thick purple. Should look like something like this. So notice this purple graph, the purple line that I just drew in, has all the exact points, the critical values and the inflection points. And it has summarized all the information from the first derivative test, the second derivative test, and the test for concavity. Okay? Will I be a stickler for exactness here? No. This is definitely a rough sketch. Okay. However, right, I will critique, right, how heavily you conclude stuff using the information that's been provided. Got it? Okay. So now the big reveal. I've got a guess, right? That purple line that I just put down, I'm thinking is what my graph is supposed to look like. Okay. So let's go to Desmos. F of x is equal to x squared e to the x. Bam. Space this out a little bit so that everybody can see. There we go. Yeah? And let's go ahead and double check our guess. That was my guess. That is the actual. Not too far off, huh? So let's do that again. Guess. Actual. All of this solely by taking derivatives and finding points. Okay? This is the analytic geometry portion of your course. Okay? Cool stuff. Cool stuff, huh? Cool stuff. All right. A couple things. If you take a look at my guess, right, versus the actual, notice that the actual actually does not dip below the x-axis. It actually becomes very asymptotic there. Yeah? Okay. As opposed to my guess, where I do make it dip below the x-axis, and that's fine. Regardless of that, though, my guess is pretty darn solid. Hopefully you guys see that. It's a pretty darn solid guess, right? And this is what I'm saying, like, am I going to be nitpicky on your guess versus the actual? No, not too nitpicky, right? This was supposed to be a rough sketch, right? However, you should be able to pick apart and analyze all portions of a function using just the first and second derivatives, okay? Whew, that was a long, long video. That was a long example, okay? After this, I've got you guys doing the last quick check, okay? Here, I'm providing the graph for everybody down here. Give it an honest to goodness attempt. Use your first derivative info, use your second derivative info to try to get yourself a decent rough sketch of your function. Okay, and then verify using Desmos. Okay, like I said, there's no penalty for being wrong here. I'm actually I want you guys to try it out. Okay. Okay. After that, lecture questions. If you got any questions on the stuff that I just covered, ask me during our quick check time. Come downstairs to the tutoring center, or come find me at my office. Okay. Besides that, happy studying.